Hello guys, in this video I'm gonna explain how to do a maximum power transfer in AC circuits. Okay, and again we're gonna explain this through an example. So let's review first what is the definition, what is the idea behind the maximum power transfer. Okay, so let's go back to like the DC circuits. If you have like a source, voltage source, let's call it VS for example, and it has like an internal resistance RS, R source. And we connect that source to some load, some resistance R load. So if you review textbook or in textbooks actually, okay, it's not always RL receives the maximum power from the source. At certain condition, RL will receive this maximum power. Okay, basically it will have like the maximum efficiency at that time. And this condition is that RS must be equal to R load, or R load must be equal to RS, whatever. So that's the condition. So if you know the internal resistance of the source, voltage source, for example, okay, if you then you tune your load such that the load equal to the internal resistance, at that moment you know that your load will receive the maximum power. And this maximum power B average will be equal to, in DC circuits, Vs square over 4R load. Where is that? That's for DC circuits. What about the AC circuits? In AC circuits, it's a little bit different because generally you have like an inductive, you have reactance, you have impedance, you have imaginary part, either from a capacitor or an inductor or both, and you have like resistance part or real part, which is resistance. Okay, so we have a Vs again. This Vs is variable. You know, it's a cosine wave, for example, sinusoidal. Then you have an internal impedance Zs, and you have a load Zl. Ds generally equal to Rs plus J XS. X can be like positive, it's an inductor, if it's an inductor, or negative if it's like a capacitor. And ZL, the load, equal to RL plus J XL. Again, XL might be from an inductor, at that time it will be positive, or from a capacitor, and at that time it will be, or a combination of both actually. Okay, so what is the condition here? For maximum power transfer, it's not that ZS equal to ZL like the DC circuits. No, DS should be equal to ZL conjugate. That means RS must be equal to RL, and XS must be equal to minus XL. Conjugate means it gives the sign of like the imaginary part. So XL equal to minus XL or XS, or XS minus equal to minus XL, whatever you want. Okay, that's the condition. At that time, P average, maximum power here, will be equal to very similar like equation like that. But remember, in DC circuits, RMS is actually the case. Here we have like a variable, we have amplitude V maximum, for example, cosine omega t, and the VRMS is equal to V maximum over square root of 2. Okay, and we need the RMS here. So it's equal to V amplitude square over 2 for the RMS. Then over 4 RL. So in general, it will be Vs magnitude square over 8 RL. That's the maximum power that you can deliver to resistive component of a load. Okay? Remember the power in inductor or a capacitor is not stored, it is not consumed, it's stored. It will be alternatingly, going forward and backward from the source and the inductor or the capacitor. Okay, so let's have an example. So in that example here from your book, it's again a problem. So we have a circuit and it's in a phasor domain here, and it asks you to choose the load impedance L so that the power distributed in it is maximum. Okay, how much power will be? So determine ZL. Actually, we need just the resistive part. Okay, and determines the maximum power transfer. Everything else is given. Okay, to determine the power, the maximum power, we need to know the impedance between like the source and like the load. I said something that might a little bit confuse you. I said ZS the source internal resistance. It doesn't have to be internal resistance. Okay, but I mean if you have like a source, just a source, and you connect it directly to a load, that case there is nothing in between. Okay, then it will be the internal resistance. Okay, but generally, if you have a load and you have like some other component connected to the source and you have your source, then D load or R load should equal to the resistive component of all the resistance between its terminals and the source, like Thevenin equivalent. And that's why Thevenin is a must in AC circuits or DC circuits. Okay, so to determine D load that will receive maximum power, we have to reduce the circuit into the Thevenin equivalent. We must do that. We must. So we're gonna call this terminal A, we're gonna call this terminal B. So we're gonna have the Thevenin equivalent between A and B, basically, if we look like that. Okay? Good. So to determine the Thevenin, that's a very good practice to it. So we have two components. We have this Thevenin, number one, finding this Thevenin. In that, we cancel all the sources. We have here only one source, which is a voltage source. To cancel a source, we cancel its effect. So let's draw the circuit first. So here is A, here is B. We have here minus G4. We have the reactance G2. We have 4 ohms. Then the source. We want to cancel the source. We cancel a source. This is the voltage source. We cancel its effect. The effect of the voltage source, it raises the voltage of that point, that node, positive node, over the negative node by 20. But to cancel it, you have to do a short circuit. Because if you have a short circuit between 2 points, 2 nodes, they're going to have the same voltage. So you cancel basically the effect of raising the voltage. You're going to put basically a short circuit. Just like that. Okay? Just like that. So if we look now between the two terminals, A and B, basically Z7 will be 4 parallel with G2, and both of them series with minus G4. So it's equal to 4 multiplied by G2 over 4 plus G2, this is the parallel, minus G4. Okay? You can also, this is the easy way because the circuit is easy. You might also have a general way to do it, which we explained in the previous video. If you want to review, please go and review it back. So in a previous video, we explained like a general method to do the Thevenin equivalent. I'm going to explain it again here. It's the same. We have here the 4, we have here the 2. So we put like a source between A and B. We call this source, for example, Vx, you can call it whatever you like. And this source produces Ix. And Z7, so another solution here, another solution. Z7 is equal to Vx divided by Ix. Okay? So Ix is going that way here. So Ix actually equal to Vx over the combination of the whole impedance, which is basically what we just mentioned. Okay, 4 multiplied by G2 over 4 plus G2 minus G4. Okay, so if we divide by Ix both ways, so 1 will be equal to Z7 divided by 4 multiplied by G2 over 4 plus G2 minus G4. From that, Z7 will be equal to 4 multiplied by G2 over 4 plus G2 minus G4. Just like what we did. Okay? We need to simplify this. So Z7 equal to our online calculator to do that calculation. Our online complex number calculator. Let me get it. Okay. So here it is. So we need 4. So 4 multiplied by G2 is G8. So in parentheses, 8i. We're going to divide by 4 plus G2. 4 plus 2i. And put all of that in a parentheses. And then subtract minus 4i. G4. 8. That's very easy. So 7 is that here, which is 0.8 ohms minus 0.8 minus 2.4 J ohms. That's the 7. Okay. Compared to my solution, yes, it's correct. Good. Number 2. V7. V7 is the V open circuit between A and B. So and we're gonna keep the sources. So we have the minus G4. And now here is A, here is B, and that's open circuit. Important. Okay. Here we have G2. Here we have the 4 ohms. Here we have our source. And our source was 20. 20 angle 0 is just 20. No phase difference, basically. And that's open circuit. So the current here, IAB. So IAB equal to 0. That means the current that comes out of the 20-volt source just goes like that. So basically 4 and the G2 are in series. 4 ohms and G2 ohms are in series. Okay. Let's determine this current. Let's call it I. So I is equal to 20 divided by 4 plus G2. Okay, good. Do we want I? No, we don't want I. We want the V7. V7 is the V open circuit, that voltage between A and B. Okay. So let's have a loop. That loop here and apply Kirchhoff. Okay. So the current IAB is passing through minus G4 in that way. The current I is passing from top to bottom of G2, so the voltage that will be in that way. Okay, so KVL will give us VAB, which is V Thevenin, plus IEB multiplied by minus G4. That's the voltage across the capacitor. Minus, because it's the opposite direction, the voltage across G2, which is I, the current, multiplied by G2. Remember, IEB is equal to 0 because between A and B there is an open circuit. From that, VEB, which is V Thevenin, is equal to I multiplied by G2. So V Thevenin equal to I. What is I? It's 20 divided by 4 plus G2. That's why we started by I, multiplied by G2. That's V7. Let's calculate V7 now. So V7 is 20 divided by 4 plus G2. 20 divided by 4 plus G2. Multiplied by G2. 5. 4 plus 8i. Let's copy that. 63.43. So as a rectangular form, it's 4 plus 8i for 8j. And why we don't call it, why we use the symbol J in AC circuits, not to confuse ourselves with the symbol I, which usually represents the current. That's why we use J. Okay, or you can say 8.94 angle 63 point. That's good. Yeah. Angle what? Angle 43. That's V7. Okay. Now we can find the resistance Z load and also the power maximum power transfer. So now Z load, remember for maximum power transferred, we have the equivalent circuit like that. V7, V7, and our Z load that's unknown. For maximum power transferred, Z load must be equal to Z Thevenin conjugate. So it will be equal to 0.8, then plus the conjugate, you flip the sign of the measurable, 2.4 J. Okay. And the maximum power B maximum delivered to our load, okay, is basically V Thevenin square divided by 8 multiplied by R load. This is R load. 0.8. Okay. So 8.94, this is the magnitude of the V Thevenin divided by 8 multiplied by 0.8. Let me review this. That looks, yeah, that looks good. So the answer is 12.488 watts. Okay, guys, that's basically, you know, the how to design basically a load such that you deliver a maximum power to that load. And here is how an example basically from AC circuits. Thank you very much for watching and see you in another video. Bye-bye.